Tonight, we're going to take a journey through our solar system, but not in the way you might expect. We're not just going to talk about planets and moons. We're going to understand the true scale of our cosmic neighborhood. Because here's the thing most people don't realize. When you see diagrams of the solar system in textbooks or online, they're lying to you, not intentionally, but out of necessity. The real distances involved are so immense that if you drew everything to scale, you couldn't fit it on a page or a poster or even on a football field. And by the end of this journey, you're going to understand just how much nothing surrounds us. Before we start, if you enjoy these deep dives into space, a quick like or subscribe would really help this channel grow. Now, let's begin. Let's start with what you think you know. You've probably seen countless images of the solar system. 8 planets arranged in a neat line, maybe with the asteroid belt between Mars and Jupiter, all circling a central star that looks about the same size as Jupiter. These pictures are useful for showing what's in our solar system. But they're completely wrong about scale. If those pictures were accurate, if the planets were really that close together compared to their sizes, everything would be different. Worlds would be pulling on each other with their gravity. Collisions would be common. The night sky from Earth would be filled with giant disks of neighboring planets. But that's not what we see. When you look up at night, the planets look like bright stars. Even Venus, the brightest and our closest neighbor, appears as just a point of light. There's a reason for that. The distances between worlds are staggering compared to their sizes. Let's put this in perspective with a simple example. If you had a basketball to represent our star and placed it in the center of a room, where would you put Earth? Most people would guess somewhere in the same room, maybe a few meters away. The real answer? Earth would be a tiny ball about 2 millimeters across, roughly the size of a small bead, and you'd have to place it about 26 meters or 85 feet away. That's the length of about 2 school buses parked end to end. And that's just Earth, the third planet. Neptune, the most distant planet, would be about 900 meters, or almost 3,000 feet away. That's more than half a mile. You'd need a football stadium to properly show this scale, and most of it would be nothing but air. Before we can appreciate the scale of the solar system, we need to start with something familiar. Let's start with Earth. Our planet measures about 12,742 kilometers, or 7,918 miles across. That seems large. If you wanted to walk around the equator, walking 8 hours a day at a steady pace, it would take you more than a year. If you drove non-stop at highway speed, it would still take about 2 weeks. From our perspective on the surface, Earth feels enormous. There are oceans that stretch beyond the horizon, mountains that take days to climb, continents separated by thousands of kilometers of open water. You could spend your entire life traveling and still not see everything. But Earth is just one planet. And compared to some of the other objects in our solar system, it's actually quite small. The closest object to Earth, other than artificial satellites, is the Moon. It circles us at an average distance of about 384,400 kilometers or 238,855 miles. Let's make that distance more concrete. Light travels at about 300,000 kilometers or 186,000 miles per second. That means light from the Moon takes about 1.3 seconds to reach Earth. When you look at the Moon, you're seeing it as it was just over a second ago. Astronauts who traveled to the Moon during the Apollo missions between 1969 and 1972 took about 3 days to get there. The fastest spacecraft we've ever built, the New Horizons probe, would make the trip in about 8 hours. Now here's something interesting. If you wanted to line up planets between Earth and the Moon, you could fit all 7 other worlds in our solar system in that gap. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune, if you place them side by side, would stretch about 390,000 kilometers or 242,000 miles. That's just slightly more than the distance to the Moon. Think about that. The space between Earth and our Moon is wide enough to contain every other planet lined up. That's how much nothing there is, even in this tiny corner of our cosmic neighborhood. Now let's talk about our star, because understanding its size is crucial to grasping the scale of everything else. Our central star is staggering in size. It measures about 1,392,000 kilometers, or 865,000 miles across. That's about 109 times wider than Earth. If Earth were a grape, our star would be a sphere about 2.4 meters or 8 feet across. But diameter doesn't tell the whole story. Volume gives you a better sense of the size difference. About 1.3 million Earths would fit inside. Imagine trying to fill it with Earths, like filling a jar with marbles. You'd need 1,300,000 of them, and there would still be space left over. Our star also contains 99.86% of all the mass in the solar system. Everything else, all 8 planets, all the moons, all the asteroids, all the comets, all the dust, everything together makes up less than 0.2%. This central body dominates not just in size, but in mass. Every second, it converts about 4 million tons of matter into energy through nuclear fusion. This energy radiates outward in all directions. The tiny fraction that hits Earth is enough to drive our weather, power photosynthesis in plants, and warm the surface to temperatures that allow liquid water to exist. The scale is so large that if you were standing on its surface and looking at the horizon, that horizon would be about 30 times farther away than Earth's horizon is from sea level. The surface area is about 12,000 times greater than Earth's. You could wrap our entire planet's surface around it 12,000 times and still not cover it completely. Now that we understand our star's size, let's look at the planets, starting with the inner solar system. This region contains 4 rocky worlds: Mercury, Venus, Earth, and Mars. These are called terrestrial planets because they have solid surfaces you could theoretically stand on. Mercury circles closest to our central star at an average distance of about 58 million kilometers or 36 million miles. We measure distances in the solar system using a unit called an astronomical unit, or AU. 1 AU is the average distance from Earth outward, about 150 million kilometers or 93 million miles. So Mercury travels at about 0.39 AU. The smallest planet in our solar system, Mercury measures about 4,879 kilometers or 3,032 miles across. That's about 38% the size of Earth. If Earth is a grape, Mercury is a large peppercorn. What's interesting about Mercury is how slowly it rotates. One day on Mercury, the time it takes to spin once on its axis lasts about 58 Earth days, but it completes an orbit quickly, in about 88 Earth days. This creates a strange situation. Because it rotates slowly while traveling around our star relatively fast, one solar day on Mercury, from sunrise to sunrise, actually lasts about 176 Earth days. That's 2 Mercury years for every single day-night cycle. Mercury's surface temperature swings are extreme. During the day, temperatures can reach 430 degrees Celsius or 806 degrees Fahrenheit. At night, they drop to minus 180 degrees Celsius or minus 292 degrees Fahrenheit. That's a temperature swing of about 610 degrees Celsius or 1098 degrees Fahrenheit more than any other planet. Venus travels next at about 0.72 AU or 108 million kilometers, which equals 67 million miles. Venus is almost identical in size to Earth, measuring about 12,104 kilometers or 7,521 miles across. That's about 95% of Earth's width. Venus is often called Earth's twin because of the similar size, but the similarities end there. Venus has a thick atmosphere made of carbon dioxide that creates a runaway greenhouse effect. The surface temperature reaches about 470 degrees Celsius or 878 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure at the surface is about 92 times greater than Earth's. If you stood on Venus, you'd be crushed and cooked simultaneously. Venus also rotates backwards compared to most planets. While Earth rotates from west to east, Venus rotates from east to west, so sunrise happens in the west on Venus. Even stranger, Venus rotates very slowly. One day on Venus lasts about 243 Earth days. But Venus completes one orbit in about 225 Earth days. This means a day on Venus is actually longer than a year on Venus. Earth, as we've discussed, travels at 1 AU. We'll come back to our planet later when we talk about what makes it special. Mars, the fourth world, circles at about 1.52 AU or 228 million kilometers, equal to 142 million miles. Mars measures about 6,792 kilometers, or 4,220 miles across, roughly half the size of Earth. Mars is sometimes called the red planet because iron oxide, basically rust, covers much of its surface. The average temperature sits at about minus 63 degrees Celsius, or minus 81 degrees Fahrenheit, much colder than Earth. One of the most impressive features on Mars is Olympus Mons, the largest volcano in the solar system. It stands about 21 kilometers or 13 miles high, roughly 2.5 times the height of Mount Everest. The base of Olympus Mons spans about 600 kilometers or 370 miles across. If you stood at the base, you couldn't see the summit because it would be beyond the horizon. Mars also has the largest canyon system we know. Valles Marineris stretches about 4,000 kilometers or 2,500 miles long. If it were on Earth, it would span the entire United States from coast to coast. In places, this canyon is about 200 kilometers or 125 miles wide, and up to 7 kilometers or 4.3 miles deep. Between Mars and Jupiter lies the asteroid belt, a region filled with rocky objects. Despite what science fiction movies might show, this belt is mostly nothing. If you flew a spacecraft through it, you probably wouldn't even see an asteroid with your own eyes. They're spread out over such an area that encounters are rare. The asteroid belt extends from about 2.2 AU to about 3.2 AU. That's a region about 150 million kilometers or 93 million miles wide. Within this space, there are millions of asteroids, but most are quite small. The largest object here is Ceres, now classified as a dwarf planet. Ceres measures about 940 kilometers or 584 miles across. Despite being the largest object in the belt, Ceres is much smaller than any of the 8 major planets. If you could somehow gather all the asteroids in the belt and combine them into one object, the total mass would be only about 4% of the Moon's mass. The entire asteroid belt contains less material than our Moon. This tells you something important. The asteroid belt isn't the remains of a destroyed planet. It's actually material that never formed into a planet in the first place, probably because Jupiter's gravity disrupted the formation process billions of years ago. Now we come to Jupiter, And this is where the scale really starts to change. Jupiter circles at about 5.2 AU, which is roughly 778 million kilometers or 484 million miles. That's more than 5 times farther out than Earth. Jupiter is staggering. It measures about 139,820 kilometers, or 86,881 miles across. That's about 11 times wider than Earth. If Earth were a marble, Jupiter would be a basketball. But the real difference is in volume. Jupiter's interior is so vast that more than 1,300 Earths would fit inside with room to spare. Jupiter's mass is about 318 times that of Earth. Jupiter is so heavy that it contains more than twice the mass of all the other planets combined. Jupiter doesn't have a solid surface like Earth. It's a gas giant, composed mostly of hydrogen and helium. If you tried to land on Jupiter, you'd just keep sinking deeper and deeper into increasingly dense gas until the pressure would crush any spacecraft. Deep inside, there might be a rocky core, but we're not entirely sure. The Great Red Spot on Jupiter is a storm that's been raging for at least 400 years. Early astronomers spotted it through telescopes in the 1600s, and it's still there today. This storm is bigger than Earth. Our entire planet would fit inside the Great Red Spot with room around the edges. Wind speeds at the storm's edge reach about 432 kilometers per hour or 268 miles per hour. Jupiter rotates incredibly fast for such a large planet. One day on Jupiter lasts only 9 hours and 56 minutes. This rapid rotation causes Jupiter to bulge at the equator. The planet is noticeably flatter at the poles than it is wide at the equator. Jupiter has at least 79 known moons, and scientists keep discovering more. The 4 largest moons, discovered by Galileo Galilei in 1610, are Io, Europa, Ganymede, and Callisto. Io is the most volcanically active body in the solar system. It has hundreds of active volcanoes constantly reshaping its surface. The volcanic activity is driven by tidal heating. Jupiter's gravity squeezes and stretches Io as it travels, generating heat through friction. Europa is one of the most exciting places in the solar system for the search for life. It has a smooth, icy surface, but scientists are confident there's a global ocean of liquid water beneath that ice. This subsurface ocean might contain twice as much water as all of Earth's oceans combined, kept liquid by tidal heating from Jupiter. Europa is smaller than our moon, but it might harbor more liquid water than our entire planet. Later missions found that Saturn's moon Enceladus also has a subsurface ocean with geysers shooting water into space, and scientists suspect several other moons, including Ganymede and Callisto, might have buried oceans as well. Ganymede is the largest moon in the solar system, even larger than the planet Mercury. It measures about 5,268 kilometers or 3,273 miles across. Ganymede is the only moon known to have its own magnetic field. Callisto is heavily cratered, preserving a record of impacts from billions of years ago. These 4 moons alone make Jupiter like a miniature solar system. They're fascinating worlds in their own right, each deserving its own detailed study. Saturn travels at about 9.5 AU, or 1.4 billion kilometers, which is 870 million miles. That's nearly twice as far out as Jupiter. Saturn measures about 116,460 kilometers, or 72,366 miles across. That's about 9.5 times wider than Earth. Saturn's volume is enormous, with space for about 760 Earths packed inside. Like Jupiter, Saturn is a gas giant composed mostly of hydrogen and helium. Saturn is actually the least dense planet in the solar system. If you could find a bathtub large enough, Saturn would float in the water. Saturn is famous for its spectacular ring system. These rings are made of billions of chunks of ice and rock, ranging in size from tiny grains to pieces as large as houses and even mountains. The rings extend hundreds of thousands of kilometers from the planet, but are surprisingly thin. In some places, the rings are only about 10 meters or 33 feet thick. The main rings are divided into several sections. The A ring, B ring, and C ring are the most prominent. Between the A and B rings is a gap called the Cassini division, named after the astronomer Giovanni Cassini, who discovered it in 1675. This gap is about 4,700 kilometers or 2,920 miles wide. Scientists aren't entirely sure how old Saturn's rings are. They might be relatively young, perhaps only a few 100 million years old. The rings are gradually disappearing as ice particles slowly fall into Saturn's atmosphere. In a few 100 million years, Saturn might not have rings at all. Saturn itself has some remarkable features. At the North Pole, there's a hexagonal cloud pattern about 30,000 kilometers or 18,640 miles across. This hexagon has been observed for decades, and scientists think it's created by a jet stream. But the exact mechanism that produces such a perfectly geometric shape is still mysterious. Saturn has at least 146 known moons, more than any other planet we know. The largest moon, Titan, is bigger than Mercury and measures about 5,150 kilometers or 3,200 miles across. Titan is the only moon in the solar system with a thick atmosphere denser than Earth's. The atmosphere is mostly nitrogen with some methane. Titan's surface has lakes and rivers, but they're not filled with water. They contain liquid methane and ethane. The temperature on Titan's surface is about -179 degrees Celsius or -290 degrees Fahrenheit, cold enough that methane exists as a liquid. Another fascinating moon is Enceladus, which is only about 500 kilometers or 311 miles across. Despite its small size, Enceladus has geysers at its south pole that shoot water vapor and ice particles into space, fed by its subsurface ocean. The Cassini spacecraft flew through these plumes and detected organic molecules. Uranus circles at about 19.2 AU, roughly 2.9 billion kilometers or 1.8 billion miles out. At this distance, Uranus takes about 84 Earth years to complete one orbit. Uranus measures about 50,724 kilometers or 31,518 miles across, about 4 times Earth's width. By volume, roughly 63 Earths would fill Uranus's interior. What makes Uranus unique is its extreme axial tilt. While most planets spin like tops, Uranus is tilted on its side at about 98 degrees. The planet essentially rolls along its orbit like a ball. This creates the most extreme seasons in the solar system. Each pole takes turns facing our star for about 42 Earth years at a time. During this period, one pole experiences continuous daylight while the other is in complete darkness. Uranus is classified as an ice giant rather than a gas giant. It's composed mostly of water, methane, and ammonia in various states, with a relatively small rocky core. The methane in its atmosphere absorbs red light and reflects blue and green light, giving the planet its distinctive pale blue color. Uranus was the first planet discovered with a telescope. William Herschel discovered it in 1781. The discovery of Uranus instantly doubled the known size of the solar system. Uranus has 27 known moons and a faint ring system discovered in 1977. Neptune travels farthest, at about 30 AU, which is roughly 4.5 billion kilometers, or 2.8 billion miles out. At this distance, Neptune takes about 165 Earth years to complete one orbit. Neptune measures about 49,244 kilometers or 30,599 miles across, slightly smaller than Uranus. Its interior volume holds about 58 Earths. Like Uranus, Neptune is an ice giant. But Neptune is more visually interesting because it has more dynamic weather. Neptune has the strongest winds in the solar system, with speeds reaching up to 2,100 kilometers per hour or 1,300 miles per hour. That's faster than the speed of sound on Earth. Neptune's deep blue color is more vivid than Uranus's because Neptune has more methane in its upper atmosphere. The planet also has visible features like the Great Dark Spot, a storm system observed by Voyager 2 in 1989. What's puzzling about Neptune is how it has such energetic weather despite being so far out. Neptune receives very little energy, about 900 times less than Earth does. Scientists think Neptune must have a strong internal heat source, driving its atmospheric dynamics. Neptune was discovered in 1846 through mathematical predictions. Astronomers noticed that Uranus's orbit didn't match predictions, calculated where another planet would need to be, pointed their telescopes at that location, and found Neptune. Neptune has 14 known moons. The largest, Triton, travels backwards, suggesting it was captured by Neptune's gravity. Triton is geologically active with nitrogen geysers and is slowly spiraling inward. In a few billion years, Neptune's gravity will tear Triton apart, possibly creating a magnificent ring system. Now that we've toured all 8 planets, let's step back. We've talked about sizes and distances, but it's hard to keep all these numbers in your head. Let's use a way to visualize this that really drives home how far apart everything is. Imagine you're driving across the United States from New York to Los Angeles, a distance of about 4,500 kilometers or 2,800 miles. If our central star was sitting in New York's Times Square, where would the planets be along your route? Mercury would be in Philadelphia, about 140 kilometers or 87 miles away. Venus would be somewhere around Pittsburgh, about 500 kilometers or 300 miles from New York. Earth would be near Cleveland, Ohio, about 750 kilometers or 465 miles away. Mars would be in Chicago, about 1,200 kilometers or 745 miles from New York. Jupiter would be past Denver, about 2,500 kilometers or 1,550 miles away. Saturn would be somewhere in Nevada, getting close to the west coast. Uranus would require you to continue past Los Angeles out into the Pacific Ocean. Neptune would be somewhere near Hawaii. This cross-country trip shows you how the distances scale up dramatically as you move outward. The inner solar system fits within the eastern half of the United States, but the outer solar system stretches thousands of kilometers beyond, and we haven't even reached the edge yet. Here's what all these distances tell us. The solar system is dominated by nothing. If you randomly picked a point somewhere within Neptune's orbit, the overwhelming odds are you'd find yourself in a void. Even the asteroid belt consists mostly of gaps between objects. If you were in a spacecraft traveling through it, you'd probably have to intentionally navigate to see one up close. Objects are separated by hundreds of thousands of kilometers. This is hard for our brains to grasp because we live in a world full of things, buildings, trees, cars, people, all packed relatively close together. But the solar system operates on a completely different scale. The distances are so immense that even light, traveling at 300,000 kilometers or 186,000 miles per second, takes hours to cross. Let's think about the solar system in terms of light travel time, because this gives another perspective on the scale. Light from our central star takes about 8 minutes and 20 seconds to reach Earth. By the time you see that bright disk in the sky, you're seeing it as it was 8 minutes ago. Light takes about 43 minutes to reach Jupiter. It takes about 4 hours to reach Neptune. If our star suddenly vanished, we wouldn't know about it for 8 minutes. For those 8 minutes, Earth would continue its orbit around nothing, receiving light that was already on its way. Then, suddenly, the light would cut off, and Earth would begin moving in a straight line. From our star to Mercury, about 3 minutes. To Venus, about 6 minutes. To Mars, about 12 minutes. To Saturn, about 80 minutes. To Uranus, about 2 hours and 40 minutes. These times might not sound that long until you remember that we're talking about light, the fastest thing in the universe. Nothing can travel faster. So these times represent the absolute minimum it would take for anything to travel between these locations. For human spacecraft, the times are much longer. The Voyager 1 spacecraft, launched in 1977, took about 40 years to reach the edge of the solar system and enter interstellar space. Both Voyager spacecraft are still traveling outward, moving at about 17 kilometers per second or about 38,000 miles per hour. At this speed, they won't reach another star for tens of thousands of years. Let's talk about how long it would take to travel to different planets using current technology. The Apollo missions to the Moon took about 3 days each way. The Moon is about 384,000 kilometers, or 238,000 miles away. Mars is much farther. The distance between Earth and Mars varies depending on where both planets are in their orbits. At their closest approach, Mars is about 55 million kilometers, or 34 million miles from Earth. At their most distant, they're about 400 million kilometers, or 250 million miles apart. Spacecraft traveling to Mars typically take between 6 to 9 months. NASA's Perseverance rover, which landed in February of 2021, took about 7 months to get there. Jupiter is even farther. The Galileo spacecraft, launched in 1989, took 6 years to reach Jupiter. The Juno spacecraft, launched in 2011, took 5 years. Saturn is more distant still. The Cassini spacecraft, launched in 1997, took 7 years to reach Saturn, arriving in 2004. No spacecraft has ever been specifically sent to Uranus or Neptune. The only close-up observations we have come from Voyager 2, which flew past Uranus in 1986, and Neptune in 1989. Voyager 2 launched in 1977, so it took 9 years to reach Uranus and 12 years to reach Neptune. Let's think about speed for a moment, because understanding speed helps us appreciate the distances involved. The fastest manned vehicle ever built was the Apollo 10 command module during its return from the Moon in May of 1969. It reached a speed of about 39,900 kilometers per hour, or about 24,791 miles per hour. At that speed, you could travel from New York to Los Angeles in about 6 minutes. But even at that incredible speed, it would take about 43 days to reach our star, about 4 years to reach Jupiter, about 8 years to reach Saturn, and about 17 years to reach Neptune. The fastest unmanned spacecraft we've built is the Parker Solar Probe, launched in 2018. At its fastest, the Parker Solar Probe reaches speeds of about 690,000 kilometers per hour, or 429,000 miles per hour. At that speed, it could travel from New York to Los Angeles in about 7 seconds. Even at this incredible speed, it would still take about 2.5 days to reach our central star, about 2 months to reach Jupiter, about 4 months to reach Saturn, and about 9 months to reach Neptune. These numbers show you that even with our best technology, the solar system is staggering in size. The distances between planets are so large that journeys take months or years. Let's think about speed for a moment, because understanding speed helps us appreciate the distances involved. The fastest manned vehicle ever built was the Apollo 10 command module during its return from the Moon in May of 1969. It reached a speed of about 39,900 kilometers per hour, or about 24,791 miles per hour. At that speed, you could travel from New York to Los Angeles in about 6 minutes. But even at that incredible speed, it would take about 43 days to reach our star, about 4 years to reach Jupiter, about 8 years to reach Saturn, and about 17 years to reach Neptune. The fastest unmanned spacecraft we've built is the Parker Solar Probe, launched in 2018. At its fastest, the Parker Solar Probe reaches speeds of about 690,000 kilometers per hour, or 429,000 miles per hour. At that speed, it could travel from New York to Los Angeles in about 7 seconds. Even at this incredible speed, it would still take about 2.5 days to reach our central star, about 2 months to reach Jupiter, about 4 months to reach Saturn, and about 9 months to reach Neptune. These numbers show you that even with our best technology, the solar system is staggering in size. The distances between planets are so large that journeys take months or years. We've talked about the 8 planets, but the solar system doesn't end at Neptune. Beyond Neptune lies the Kuiper belt, a region filled with icy bodies left over from formation billions of years ago. The Kuiper belt extends from about 30 AU to about 50 AU. In comparison, Neptune travels at 30 AU. So the Kuiper belt begins right at Neptune's orbit and extends outward for another 150 million kilometers, or 93 million miles. The Kuiper belt contains thousands of known objects and probably hundreds of thousands more waiting to be discovered. Most are small, just a few kilometers across, but some are quite large. Pluto is the most famous Kuiper belt object. Pluto circles at an average distance of about 39.5 AU, which is roughly 5.9 billion kilometers, or 3.7 billion miles. Pluto takes about 248 Earth years to complete one orbit. Pluto measures about 2,377 kilometers, or 1,477 miles across, smaller than Earth's moon. When Pluto was discovered in 1930 by Clyde Tombaugh, it was classified as the 9th planet. It held that designation for 76 years. But in 2006, the International Astronomical Union redefined what makes a planet. Under the new definition, Pluto didn't qualify because it hasn't cleared its orbit of other debris. Pluto was reclassified as a dwarf planet. This decision upset many people who had grown up learning about 9 planets, but the reclassification made sense scientifically. Once astronomers started discovering other objects similar to Pluto in the outer solar system, they faced a choice. Either include all these objects as planets, which would mean adding dozens or even hundreds, or create a new category. They chose the latter. The New Horizons spacecraft flew past Pluto in July of 2015, giving us our first close-up look. The images revealed a complex and geologically active world that surprised scientists. Pluto has mountains made of water ice that reach 3,500 meters, or 11,500 feet high. There are plains of frozen nitrogen that appear to be geologically young. There's even evidence of possible ice volcanoes, called cryovolcanoes. The most famous feature on Pluto is a large heart-shaped region called Tombaugh Regio. The left side of this heart is a smooth plain of nitrogen ice called Sputnik Planitia. This plain shows patterns that suggest convection, where warmer ice rises and cooler ice sinks, similar to how a pot of boiling water circulates. This suggests Pluto has internal heat that keeps the nitrogen ice soft enough to flow. Pluto has 5 known moons. The largest, Charon, is about half Pluto's width. That's unusual. Most moons are much smaller than their parent planets. Charon is so large relative to Pluto that some scientists consider them a binary system, 2 objects circling a common point in space between them. Charon itself is an interesting world. It has a dark, reddish pole, probably caused by methane from Pluto's atmosphere that freezes onto Charon's surface and is then chemically altered by solar radiation. Charon also has fewer craters than expected, suggesting it might have been geologically active in the past, with internal processes that resurfaced parts of the moon. Pluto's other 4 moons, Styx, Nix, Kerberos, and Hydra, are much smaller and irregularly shaped. They're probably captured Kuiper belt objects or fragments from an ancient collision. Other significant Kuiper belt objects include Eris, Makemake, and Haumea. Eris is slightly smaller than Pluto but more massive. It travels at about 68 AU on average, though its orbit is highly elliptical, taking it as far as 98 AU at its most distant point. Eris takes about 557 Earth years to complete one orbit. The discovery of Eris in 2005 was actually the main trigger for Pluto's reclassification. When astronomers found an object farther out and more massive than Pluto, they had to decide, is this the 10th planet, or do we need to rethink what we call a planet? The decision to reclassify Pluto came the following year. Eris has one known moon, Dysnomia, which is much smaller than Eris itself. By watching Dysnomia's orbit, scientists calculated Eris's mass and found it to be about 27% more massive than Pluto, even though it's slightly smaller in width. This means Eris is denser than Pluto, probably containing more rock and less ice. Makemake is slightly smaller than Pluto and travels at about 45.8 AU. It takes about 306 Earth years to complete one orbit. Makemake's surface is covered with frozen methane, which gives it a reddish color. It has one known moon, discovered in 2016, which scientists creatively named MK2. Haumea is particularly interesting because it's shaped like an egg rather than a sphere. It rotates very rapidly, completing one rotation in less than 4 hours. This rapid spin stretches Haumea into an elongated shape. The best measurements suggest Haumea is about 2,300 kilometers or 1,430 miles long, but only about 1,700 kilometers or 1,056 miles wide. What caused Haumea to spin so fast? Scientists think it might have been involved in a massive collision billions of years ago. The impact would have sent Haumea spinning and might have created the 2 known moons and a family of smaller objects that share similar orbits. Haumea also has rings, making it one of only 5 objects in the solar system known to have rings. The others are the 4 giant planets: Jupiter, Saturn, Uranus, and Neptune. Haumea's rings were discovered in 2017 when astronomers watched Haumea pass in front of a distant star. The star's light dimmed briefly before and after Haumea blocked it, revealing the presence of a ring. Beyond the Kuiper belt, at truly staggering distances, lies the Oort Cloud. This is a theoretical shell of icy objects that surrounds the entire solar system like a bubble. The Oort Cloud is thought to begin at about 2,000 AU and extend as far as 100,000 AU. To put that in perspective, 100,000 AU is about 1.6 light-years. That's about 1/3 of the distance to the nearest star. We say the Oort Cloud is theoretical because we've never actually observed it directly. It's too far away, and the objects are too small and too dark to see with current telescopes. But we infer its existence from the comets we see. Long-period comets, comets that take hundreds or thousands of years to complete their orbits, are thought to originate from the Oort Cloud. Sometimes gravitational disturbances from passing stars or giant molecular clouds nudge these icy bodies, sending them falling toward the inner solar system. The famous Halley's Comet, which appears in Earth's sky about every 76 years, is thought to have originated from the Oort Cloud before something perturbed its orbit into a shorter period. The last time Halley's Comet was visible from Earth was in 1986. It will return again in 2061. If the Oort Cloud extends to 100,000 AU, then that's the true boundary of the solar system. That's where our star's gravitational influence effectively ends. Beyond that, objects are more influenced by the gravity of other stars. The Oort Cloud might contain trillions of objects. Some estimates suggest there could be 2 trillion or more icy bodies larger than 1 kilometer across in the Oort Cloud, but they're spread across such an enormous volume that they're effectively invisible to us. The density of objects in the Oort Cloud is incredibly low. If you were standing on one Oort Cloud object, you probably wouldn't be able to see any others with the naked eye. They'd be too far away and too dark. The structure of the Oort Cloud is thought to have 2 parts. The inner Oort Cloud, also called the Hills Cloud, is a disc-shaped region. The outer Oort Cloud is more spherical, surrounding the entire solar system in all directions. This spherical distribution means that comets from the Oort Cloud can approach from any angle, not just from the plane of the planet's orbits. Understanding the Oort Cloud helps us understand the solar system's formation and evolution. The objects in the Oort Cloud are thought to have originally formed much closer in the region where the giant planets now travel. During the early solar system's chaotic period, when the giant planets were migrating, they scattered many objects outward. Some were ejected entirely. Others ended up in the Oort Cloud, where they've remained for billions of years. The Oort Cloud is also vulnerable to outside influences. When other stars pass relatively close to the solar system, their gravity can disturb the Oort Cloud, sending showers of comets into the inner solar system. This might explain periods of increased comet activity in Earth's history. Let's talk about how planets actually move through space, because understanding orbital mechanics helps us appreciate the scale. All the planets circle our central star in roughly the same plane, called the ecliptic. If you imagine the solar system as a disk, all the planetary orbits lie close to this disk. This isn't a coincidence. It's a result of how the solar system formed from a rotating disk of gas and dust. But the orbits aren't perfect circles. They're ellipses, oval shapes. Some orbits are nearly circular, like Venus and Neptune. Others are more elongated, like Mercury and Pluto. An elliptical orbit means the planet's distance changes as it travels. When the planet is closest, it's at perihelion. When it's farthest, it's at aphelion. Earth's orbit is nearly circular, so the difference between perihelion and aphelion is only about 3%. But for Mercury, the difference is about 24%. This affects how fast planets move in their orbits. When a planet is closer, it moves faster. When it's farther away, it moves slower. This is described by Kepler's second law, which states that a line from our central star to a planet sweeps out equal areas in equal times. In simpler terms, a planet speeds up when it gets closer and slows down when it gets farther away. The closer a planet is to our central star, the faster it travels overall. Mercury zips around in just 88 Earth days. Neptune takes about 165 Earth years. This relationship between distance and orbital period is described by Kepler's third law. There's also the issue of orbital inclination, how tilted a planet's orbit is compared to Earth's orbital plane. Most planets have orbits that are fairly close to the same plane. Mercury has the highest inclination among the planets at about 7 degrees. Pluto, for comparison, has an inclination of about 17 degrees, which is one reason it was reclassified as a dwarf planet rather than a full planet. Understanding these orbital mechanics is crucial for space missions. When we send a spacecraft to another planet, we can't just point it at the planet and fly straight there. The planet will have moved by the time the spacecraft arrives. Instead, mission planners use what are called Hohmann transfer orbits, which are basically the most fuel-efficient curved paths between two orbits. A Hohmann transfer orbit is like throwing a ball to someone who's moving. You don't throw it at where they are now, you throw it at where they'll be when the ball gets there. This means spacecraft can only launch to certain planets during specific launch windows when the planets are in the right positions. These launch windows occur at regular intervals. For Mars, launch windows occur about every 26 months. For Jupiter, they occur about every 13 months. Missing a launch window means waiting for the next one. This is why space missions are planned years in advance. To really understand the scale of the solar system, it helps to know how it formed. Because the structure we see today, with small rocky planets close in and giant planets farther out, is a result of processes that happened 4.6 billion years ago. The solar system formed from a giant cloud of gas and dust called the solar nebula. This cloud was about 2 light-years across and contained all the material that would eventually become our star, the planets, and everything else. Something triggered the collapse of this cloud. It might have been a shock wave from a nearby supernova, the explosion of a massive star. The shock wave compressed the cloud, and gravity did the rest. As the cloud collapsed, it began to spin faster, like a figure skater pulling in their arms. The spinning caused the cloud to flatten into a disk with a bulge at the center. Most of the material fell toward the center, where it became increasingly dense and hot. Eventually, the center became hot and dense enough for nuclear fusion to begin, and our star was born. But not all the material fell into our central star. The material in the disk began to clump together through a process called accretion, which just means particles sticking together. Tiny particles of dust collided and stuck together, forming larger and larger objects. These grew from dust grains to pebbles to boulders to small planets called planetesimals, basically baby planets. The planetesimals continued to collide and merge. In the inner solar system, where temperatures were high, only materials that could withstand heat remained solid. These were mostly metals like iron and nickel, and rocky materials called silicates. The lighter, more volatile materials, things like water and methane that turn to gas easily, were vaporized by the heat. This is why the inner planets are small and rocky. In the outer solar system, beyond what's called the frost line, temperatures were cold enough for volatile materials to condense into ice. This meant there was much more solid material available for planet building. The cores of Jupiter, Saturn, Uranus, and Neptune grew large enough that their gravity began attracting the abundant hydrogen and helium gas. Jupiter and Saturn accumulated enormous atmospheres, becoming gas giants. Uranus and Neptune, being farther out where the nebula was less dense, accumulated less gas and more ice, becoming ice giants. This entire process took about 100 million years. By about 4.6 billion years ago, the basic structure was in place. But the solar system wasn't done changing. For the next few 100 million years, the planets' orbits weren't stable. Gravitational interactions caused the giant planets to migrate, moving inward or outward from their original positions. Jupiter probably migrated inward toward our central star, then back outward. Saturn, Uranus, and Neptune migrated outward. This migration had dramatic effects. As the giant planets moved, they scattered smaller objects throughout the solar system. Some were thrown inward. Some were ejected from the solar system entirely. Some were thrown into the inner solar system, where they bombarded the young terrestrial planets. This period of heavy bombardment lasted until about 3.8 billion years ago. During this time, the inner planets, including Earth, were constantly struck by asteroids and comets. These impacts brought water and organic compounds to Earth, which might have been crucial for the origin of life. The migration of the giant planets also explains some puzzling features of the solar system. The Kuiper belt structure, with certain regions nearly devoid of objects and others more densely populated, is thought to be a result of Neptune's outward migration. Neptune swept up many objects as it moved, scattering them into different orbits. The Oort Cloud probably formed from objects that were originally in the region where the giant planets formed. As those planets migrated, they scattered these objects to the far reaches of the solar system, where they now reside. Understanding this history helps us make sense of what we see today. The structure of the solar system, the distribution of mass, the locations of the planets, all of these are consequences of events that happened billions of years ago. Asteroids are rocky bodies that circle our central star but are too small to be considered planets. Most asteroids are quite small, though there are probably millions larger than 1 kilometer or 0.6 miles across. Asteroids are classified into different types. C-type asteroids are carbonaceous and dark, making up about 75% of known asteroids. S-type asteroids are stony, made of nickel iron mixed with silicate minerals. M-type asteroids are metallic, probably cores of small planets broken apart by collisions early in the solar system's history. The asteroid belt has regions called Kirkwood gaps, where few asteroids exist. These gaps occur at orbital periods that are simple fractions of Jupiter's orbit. Jupiter's repeated gravitational tugs eventually push asteroids out of these orbits, creating gaps. Not all asteroids travel in the main belt. Near-Earth asteroids have orbits bringing them close to our planet. Scientists track these carefully because they could potentially collide with Earth. Trojan asteroids share orbits with planets, staying about 60 degrees ahead or behind. Jupiter has over 7,000 known Trojans. Some asteroids have moons. In 2022, NASA's DART mission crashed into the moon of asteroid Didymos, successfully demonstrating we could deflect a dangerous asteroid with enough warning. Several missions have returned asteroid samples to Earth. The Japanese Hayabusa missions and NASA's OSIRIS-REx brought back pristine material from the early solar system. These samples contain organic compounds and water-bearing minerals, supporting the idea that asteroids delivered ingredients for life to Earth billions of years ago. Comets are different from asteroids. While asteroids are mostly rocky or metallic, comets are made of ice mixed with rock and dust. They spend most of their time in the outer solar system. When a comet approaches our central star and heats up, ice vaporizes, creating a glowing cloud called the coma. Solar wind creates the characteristic tail. Comets can have two tails, a dust tail that curves, and an ion tail that points directly away. Comet nuclei are usually just a few kilometers across, but the coma can be hundreds of thousands of kilometers wide, and tails can stretch millions of kilometers. Short-period comets travel in less than 200 years and come from the Kuiper belt. Long-period comets have much longer orbits and come from the Oort Cloud. Halley's Comet, appearing every 76 years, is the most famous short-period comet. Ancient Chinese astronomers recorded it as far back as 240 BC. Several spacecraft have visited comets. The Rosetta mission studied comet 67P from 2014 to 2016 and even landed a probe on its surface. These missions revealed comets are more complex than simple dirty snowballs, with varied terrain and very dark surfaces. When comets pass close repeatedly, they lose their volatile materials and become inactive. These dead comets might be difficult to distinguish from asteroids. Comets likely delivered significant water to the inner planets, including Earth. They might also have delivered organic compounds, important for life's origin. When asteroids or comets break apart, fragments continue traveling. If one enters Earth's atmosphere, it's called a meteoroid. Friction heats it, creating the bright streak we call a meteor. Larger ones reaching the ground are meteorites. Meteorites come in three main types. Stony meteorites, made of silicate minerals, make up 94% of observed falls. Iron meteorites are nickel-iron alloy. Stony iron meteorites are mixtures of both, making up only 1%. Some meteorites, called chondrites, contain chondrules, droplets of molten rock from before planets formed. These primitive meteorites give us direct samples of the material that formed the solar system 4.6 billion years ago. A few meteorites found on Earth are actually pieces of the Moon, or Mars, blasted off by impacts. We know because trapped gases match Mars's atmosphere measured by rovers. The largest meteorite ever found is the Hoba meteorite in Namibia, weighing about 60 tons. The impact that created Meteor Crater in Arizona 50,000 years ago involved an object about 50 meters or 164 feet across. The most significant impact ended the dinosaur age 66 million years ago. An impactor about 10 to 15 kilometers or 6 to 9 miles across struck near Mexico, releasing energy equivalent to billions of nuclear bombs. The resulting mass extinction killed about 75% of all species. Earth is bombarded by about 100 tons of dust daily. Larger meteoroids creating visible meteors hit several times daily. Meteorites fall a few times weekly worldwide. Civilization-ending impacts happen every few tens of millions of years on average. We monitor the sky for dangerous asteroids. With years of warning, we could nudge an asteroid to change its orbit. The best defense is early detection. We've talked about our star's size and mass, but let's discuss how its influence extends throughout the solar system and beyond. Our central star doesn't just provide light and heat, it also emits a continuous stream of charged particles called the solar wind. This wind flows outward in all directions at speeds of about 400 to 800 kilometers per second, or about 250 to 500 miles per second. The solar wind is made mostly of electrons and protons. Near Earth, the density of the solar wind is only about 5 particles per cubic centimeter. That's an incredibly thin gas. But over distances, this thin flow creates significant effects. As the solar wind flows outward, it creates a bubble called the heliosphere. This bubble extends far beyond the planets. The boundary where the solar wind meets the interstellar medium is called the heliopause. This is effectively the edge of our star's direct influence. The Voyager 1 spacecraft crossed the heliopause in August of 2012, becoming the first human-made object to enter interstellar space. It was about 122 AU at the time, which is about 18 billion kilometers or 11 billion miles. Voyager 2 crossed the heliopause in November of 2018 at about 119 AU. The shape of the heliosphere is influenced by the motion of the solar system through the galaxy. Our entire system is moving at about 220 kilometers per second or 137 miles per second relative to the local interstellar medium. This creates a bow shock ahead and a tail behind, similar to how a boat creates a wake. Gravity is the force that holds the solar system together, but it does more than just keep planets in orbit. Gravitational interactions between objects create fascinating effects. Tidal forces arise because gravity gets weaker with distance. When one object circles another, the near side feels stronger gravity than the far side. This difference in gravitational pull stretches the object. On Earth, the Moon's gravity creates ocean tides. The ocean on the side facing the Moon is pulled toward it more strongly than Earth's center, creating a bulge. The ocean on the opposite side is pulled less strongly than Earth's center, also creating a bulge. As Earth rotates beneath these bulges, we experience high tides twice a day. But tidal forces affect more than just oceans. They also create friction. As Earth rotates beneath the tidal bulges, friction slows Earth's rotation. Earth's day is getting longer by about 1.7 milliseconds per century. When dinosaurs walked Earth, a day was only about 23 hours long. The energy lost by Earth's slowing rotation doesn't disappear. It's transferred to the Moon, causing the Moon to gradually move farther from Earth. The Moon is receding at about 3.8 centimeters or 1.5 inches per year. Tidal forces can be even more dramatic on other worlds. Io, Jupiter's closest large moon, experiences extreme tidal heating. As Io travels, the planet's enormous gravity squeezes and stretches the Moon. This creates friction inside Io that generates heat, making Io the most volcanically active body in the solar system. Europa, another of Jupiter's moons, is also tidally heated, though not as intensely as Io. The tidal heating keeps Europa's subsurface ocean liquid. Tidal forces can also lead to tidal locking, where an object's rotation period matches its orbital period. Our moon is tidally locked to Earth. The same face always points toward Earth because the moon rotates once per orbit. Most large moons in the solar system are tidally locked to their planets. Earth experiences seasons due to our axis tilt of 23.5 degrees. During part of our orbit, the northern hemisphere tilts toward our star, creating summer in the north and winter in the south. 6 months later, the seasons reverse. Mars has a similar axial tilt of 25 degrees, giving it seasons like Earth's. However, Mars's elliptical orbit creates complications. Mars is closer during southern summer, making southern summers shorter and hotter, while northern summers are longer and cooler. Mars also has dust storms that can cover the entire planet during southern summer. Jupiter has almost no tilt, only 3 degrees, so it doesn't have significant seasons. Its weather is dynamic for other reasons, driven by internal heat and rapid rotation. Saturn's 27-degree tilt creates pronounced seasons. Each season lasts about 7 Earth years, since Saturn takes 29 years to complete its orbit. The Cassini spacecraft observed seasonal changes during its mission, including the North Pole's hexagonal storm changing color from blue to gold. Saturn's rings also create interesting seasonal effects, casting shadows when edge-on and reflecting more light when tilted. Uranus's extreme 98-degree tilt creates the most unusual seasons. For 42 years, one pole faces our star in continuous daylight, while the other is in darkness. Scientists weren't sure how this would affect temperatures, but observations show heat is somehow redistributed across the planet, possibly by atmospheric winds. Neptune has a 28-degree tilt, similar to Earth and Saturn, However, its 165-year orbit means each season lasts about 40 years. Neptune has completed only one full orbit since its discovery in 1846. Even planets without significant tilt can have seasonal changes from elliptical orbits. Mercury's highly elliptical orbit means it receives twice as much solar energy at perihelion compared to aphelion, creating temperature variations tied to orbital position rather than axial tilt. Let's take a moment to appreciate the extraordinary achievement of sending spacecraft to explore the solar system. These missions have revolutionized our understanding of the planets and shown us worlds we could never have imagined. The first successful flyby of another planet occurred in 1962 when Mariner 2 flew past Venus. This mission confirmed that Venus had a thick carbon dioxide atmosphere and extremely high surface temperatures. Mariner 4 flew past Mars in July of 1965, returning the first close-up images of the red planet. The Pioneer 10 and 11 spacecraft, launched in 1972 and 73, were the first to visit Jupiter. Pioneer 10 reached Jupiter in December of 1973. Pioneer 11 followed a year later and then continued on to Saturn. The Voyager missions, launched in 1977, are among the most successful planetary missions ever flown. Voyager 1 visited Jupiter in March of 1979 and Saturn in November of 1980. It took stunning images of both planets and their moons, including the first detailed views of Jupiter's Great Red Spot and Saturn's rings. Voyager 2 took a longer route, visiting all 4 giant planets. It reached Jupiter in July of 1979, Saturn in August of 1981, Uranus in January of 1986, and Neptune in August of 1989. Voyager 2 remains the only spacecraft to have visited Uranus and Neptune. The images and data from the Voyager missions transformed our understanding of the outer solar system. They revealed that the moons of the giant planets were diverse and geologically active worlds in their own right, not just dead chunks of rock and ice. The Galileo mission to Jupiter, which launched in 1989 and arrived in 1995, was the first to orbit one of the giant planets. It spent 8 years studying Jupiter and its moons, making numerous close flybys of the Galilean satellites. Galileo discovered evidence for subsurface oceans on Europa, Ganymede, and Callisto, revolutionizing our understanding of where life might exist in the solar system. The Cassini-Huygens mission to Saturn, launched in 1997 and arriving in 2004, was one of the most ambitious planetary missions ever attempted. Cassini spent 13 years studying Saturn, making over 250 orbits and hundreds of close flybys of Saturn's moons. The Huygens probe, built by the European Space Agency, landed on Titan in January of 2005, returning the first images from the surface of a moon in the outer solar system. Cassini discovered new moons, new rings, and new details about Saturn's atmosphere. It flew through the geysers of Enceladus, detecting water vapor and organic molecules. It watched as Saturn progressed through its seasons. When the mission ended in September of 2017, Cassini was deliberately crashed into Saturn's atmosphere to avoid any possibility of contaminating the moons with microbes from Earth. The New Horizons mission, launched in 2006, visited Pluto in July of 2015, giving us our first close-up look at this distant dwarf planet. The images revealed a surprisingly complex and active world, with mountains, plains, and possible cryovolcanoes. After Pluto, New Horizons continued into the Kuiper belt and flew past the object Arrokoth, formerly called Ultima Thule, in January of 2019. This flyby gave us our first close-up view of a pristine Kuiper belt object. Mars has been the target of numerous missions. The Viking landers in 1976 were the first successful landings on Mars, The Pathfinder mission in 1997 included the first Mars rover, Sojourner. The Spirit and Opportunity rovers, which landed in 2004, far exceeded their planned 90-day missions. Spirit operated until 2010, while Opportunity operated until 2018, driving over 45 kilometers or 28 miles across the Martian surface. The Curiosity rover, which landed in 2012, is still operating and has driven over 30 kilometers or about 19 miles. It carries sophisticated instruments to analyze the composition of rocks and search for organic molecules. Perseverance, which landed in 2021, is collecting samples that future missions might return to Earth. It's also accompanied by Ingenuity, a small helicopter that has demonstrated that powered flight is possible in Mars's thin atmosphere. These missions show humanity's ability to overcome the challenges posed by the solar system's scale. Every mission required years of planning, sophisticated engineering, and precise navigation. Every image, every measurement, every discovery came from teams of dedicated scientists and engineers working to expand our knowledge of the cosmos. We've spent a lot of time talking about the size and scale of the solar system, but let's bring it back to Earth for a moment. Because understanding how small Earth is in this context makes it all the more remarkable that our planet is the way it is. Earth travels at exactly the right distance for liquid water to exist on its surface. This region is called the habitable zone because it's not too hot and not too cold, but just right. Venus travels just inside the inner edge of this zone, and it's too hot. Mars travels near the outer edge, and while it's within the habitable zone technically, it's too small to hold onto a thick atmosphere, so it's too cold. Earth is right in the middle, but being in the habitable zone isn't enough. Mars is in the habitable zone, and it's not habitable. Earth has several other factors working in its favor. Earth has a large moon, which is unusual for a rocky planet. The moon was probably formed about 4.5 billion years ago when a Mars-sized object called Theia collided with the early Earth. The debris from this impact eventually coalesced to form the moon. The moon's gravity stabilizes Earth's axial tilt. Without the moon, Earth's tilt would vary chaotically over millions of years, causing extreme climate swings that might prevent complex life from evolving. The moon also creates tides, which might have played a role in life's transition from ocean to land billions of years ago. Earth has a strong magnetic field generated by the churning of molten iron in its outer core. This magnetic field extends into space, creating the magnetosphere that protects us from the solar wind. Without this protection, Earth's atmosphere would gradually be stripped away over time, like what happened to Mars. Earth has plate tectonics, the movement of large sections of crust across the surface. This process recycles carbon between the atmosphere and the interior, acting like a thermostat for Earth's climate. Earth also has the right size. If Earth were much smaller, like Mars, it would have cooled more quickly and wouldn't have plate tectonics or a strong magnetic field. If Earth were much larger, like a super-Earth, it might have a thicker atmosphere and stronger gravity, which could prevent the development of land-based life. All these factors working together make Earth not just habitable, but stably habitable for billions of years. This stability has allowed life to evolve from simple, single-celled organisms to the incredible diversity we see today. Earth's atmosphere is also crucial. It's mostly nitrogen and oxygen, with small amounts of other gases. The oxygen is essential for complex life like us. But interestingly, oxygen wasn't always present in Earth's atmosphere. For the first 2 billion years of Earth's history, the atmosphere contained almost no oxygen. Oxygen only built up after photosynthetic bacteria evolved and started producing it as a waste product. The build-up of oxygen, called the Great Oxidation Event, happened about 2.4 billion years ago. This was actually a catastrophe for most life at the time because oxygen was toxic to the anaerobic organisms that dominated Earth. But it opened the door for more complex life forms that could use oxygen for energy, eventually leading to animals, plants, and us. Earth also has the right amount of water. Too much water, and the entire surface would be covered by ocean with no land. Too little water, and there might not be enough for life to get started. Earth has enough water to cover about 70% of the surface, leaving plenty of land as well. The balance between ocean and land is important for the carbon cycle and for the development of diverse ecosystems. Understanding what makes Earth special helps us search for similar planets around other stars. Since the first exoplanet was discovered circling a sun-like star in 1995, we've found thousands of planets beyond our solar system. The Kepler Space Telescope, which operated from 2009 to 2018, found over 2,600 confirmed exoplanets. Many of these are nothing like the planets in our solar system. We've found hot Jupiters, gas giants that circle closer to their stars than Mercury. We've found super-Earths, rocky planets larger than Earth but smaller than Neptune. We've found planets circling two stars at once. What we haven't found yet is an exact twin of Earth. We found planets that are roughly Earth-sized. We've found planets in their star's habitable zone. But we haven't found a planet that checks all the boxes. Right size, right distance, evidence of a magnetic field, evidence of plate tectonics, a large moon, and so on. This doesn't mean Earth-like planets don't exist. It just means they might be rare, or we haven't developed the technology to detect them yet. The methods we use to find exoplanets work best for large planets close to their stars. Small, rocky planets in Earth-like orbits are much harder to detect. The James Webb Space Telescope, launched in December of 2021, is helping us study the atmospheres of exoplanets. By analyzing the light that passes through a planet's atmosphere as it transits in front of its star, we can detect what gases are present. This could eventually allow us to find biosignatures, gases like oxygen that are produced by life. Just as the solar system has a history, it also has a future. Let's think about what lies ahead over the next several billion years. Our central star is currently about 4.6 billion years old, roughly halfway through its main sequence lifetime. For the next 5 billion years or so, it will continue burning hydrogen in its core, gradually getting slightly brighter over time. But eventually, it will run out of hydrogen in its core. When this happens in about 5 billion years, it will begin fusing hydrogen in a shell around the core. This will cause it to expand dramatically, becoming a red giant. As a red giant, our star will grow to about 250 times its current size. It will become so large that it will likely engulf Mercury and Venus entirely. Earth might survive, but it will be scorched and lifeless, all the oceans boiled away, the atmosphere stripped off. This red giant phase will last for about 1 billion years. During this time, helium will fuse into carbon and oxygen in the core. But eventually, our star will run out of helium too. Unlike more massive stars, our star isn't heavy enough to fuse carbon and oxygen. Instead, it will shed its outer layers, creating a planetary nebula, a glowing shell of gas expanding into space. What remains will be the core, now exposed. This dense hot core is called a white dwarf. It will be about the size of Earth, but contain about half the mass of the current star. It will gradually cool over trillions of years, eventually becoming a black dwarf, a cold, dark remnant. The planets will continue to circle this white dwarf, but they'll be frozen and lifeless. The solar system will effectively be dead. This is the eventual fate of our solar system. Not with a bang, but with a long, slow cooling. In about 6 billion years, the solar system, as we know it, will cease to exist. One of the most valuable things we get from understanding the scale of the solar system is a sense of wonder. When you realize how immense the distances are, it changes how you see the universe. The next time you look up at the night sky and see Jupiter or Saturn, remember that you're looking at worlds hundreds of millions or billions of kilometers away. That point of light is actually a giant planet with dozens of moons and complex weather systems. When you see Mars, remember that there are rovers on its surface right now, driving across alien terrain, analyzing rocks, searching for signs of ancient life. When you see the moon, remember that humans walked on that surface over 50 years ago. We left footprints that will last for millions of years because there's no wind or rain to erase them. All of this is part of our solar system, our cosmic neighborhood. Understanding its true scale helps us appreciate both how small we are and how much we've accomplished. In 1990, Voyager 1, which was about 6 billion kilometers or 3.7 billion miles from Earth, turned its camera back toward home and took a photograph. Earth appeared as a tiny point of light, just 0.12 pixels across, suspended in a beam of sunlight. Carl Sagan, the astronomer who suggested taking this photograph, called it the pale blue dot. He wrote, "Everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives on that tiny speck of dust, suspended in a sunbeam." This image and Sagan's words capture something important about the scale of the solar system. Earth is unimaginably small compared to the distances we've discussed. From any significant distance, our planet simply vanishes. Yet it's the only home we've ever known. Understanding this should give us perspective. The problems that seem overwhelming, the conflicts that dominate the news, the stresses of daily life, they're all happening on this tiny blue dot. In the context of the solar system, let alone the universe, they're microscopic. This doesn't mean our problems aren't real or important. They are. But it does mean that we should keep them in perspective. We're all on this small planet together, circling an ordinary star in an immense solar system. As we close this journey through the solar system, let's think about the future. What comes next? NASA and other space agencies are planning missions to return humans to the moon within the next decade. The Artemis program aims to land astronauts on the lunar surface by the mid-2020s and establish a sustainable presence there. There are plans for human missions to Mars, though these are still decades away. The challenges are enormous. A round trip to Mars would take about 2 to 3 years. Astronauts would need to survive in a cramped spacecraft for months, then work on Mars's surface in an environment with no breathable air, extreme temperature swings, and dangerous radiation. But if we can overcome these challenges, humans might walk on Mars within the lifetimes of people alive today. It would be the farthest any human has ever traveled, expanding our presence in the solar system from one small world to 2. Robotic missions will continue to explore farther. There are proposals for missions to Uranus and Neptune, which haven't been visited since Voyager 2's brief flybys in the 1980s. There are plans for missions to land on Europa or Enceladus and search for life in their subsurface oceans. Perhaps within this century, we'll know whether life exists anywhere else in the solar system. That knowledge would fundamentally change how we see our place in the cosmos. We're also getting better at detecting and characterizing exoplanets around other stars. Within the next few decades, we might find an Earth-like planet in another star's habitable zone and even detect signs of life in its atmosphere. That would be one of the most important discoveries in human history. We've covered a lot of ground tonight, from Mercury's scorched surface to Neptune's deep blue clouds, from the inner rocky planets to the distant Oort Cloud. We've used analogies and scale models to try to make the distances comprehensible. The key takeaway is this: the solar system is far larger than most people realize. The distances between planets are staggering compared to the sizes of the planets themselves. The gaps dominate everything we've discussed tonight. But within these immense distances, there are fascinating worlds. Gas giants with storms larger than Earth. Ice giants tilted on their sides with the strangest seasons imaginable. Moons with buried oceans that might harbor life. Rings made of billions of chunks of ice traveling at incredible speeds. Volcanoes that dwarf anything on Earth. Canyons that could span continents. And in the midst of all this, there's Earth. One small rocky planet, circling at just the right distance, with just the right size and composition and magnetic field and moon to make it habitable. Understanding the scale of the solar system gives us perspective. It shows us how small we are, how isolated we are, and how precious our home planet is. It shows us that space exploration is difficult and takes time, but it's worth doing because every mission expands our knowledge and our perspective on our place in the universe. The next time someone asks you how far apart the planets are, you can tell them. You can describe the true scale, how distances between worlds measure in hundreds of millions of kilometers. You can explain that light itself takes hours to cross from our star to the outer planets. And maybe, just maybe, that understanding will give them the same sense of wonder that comes from truly grasping the scale of our solar system. The wonder of knowing that we live in a cosmic neighborhood so immense that light takes hours to cross it, yet so precisely arranged that our small planet can sustain life. Thank you for joining me on this journey across billions of kilometers and billions of years. If you found this exploration valuable, please consider liking this video and subscribing to the channel. It helps me continue making these deep dives into space and science. And remember, we live on a small planet in an immense solar system. But it's our planet in our solar system, and it's full of wonders waiting to be explored. Good night, and keep looking up at the stars. We've talked a lot about spatial scale, about how small Earth is compared to stars, galaxies, and the distances involved. But there's another dimension to consider: time. The universe is about 13.8 billion years old. Earth formed about 4.5 billion years ago, roughly 1/3 the age of the universe. For the first 9 billion years or so after the Big Bang, Earth didn't exist. Our central star didn't exist. The solar system didn't exist. Modern humans, Homo sapiens, have existed for about 300,000 years. That's 0.007% of Earth's history. It's 0.002% of the universe's history. All of recorded human history, from the first writing systems in ancient Mesopotamia about 5,000 years ago to today, represents only 0.001% of Earth's history. Your lifetime, if you live to be 80 years old, is 0.0000002% of the universe's history. That's 1 to 100 millionths of 1%. We exist for the briefest moment in cosmic time. Earth itself exists for only a fraction of cosmic time. Everything we know, everything we've experienced, has happened in the tiniest sliver of the universe's history. And this is just the past. The universe has a long future ahead of it. Our central star will continue to shine for about another 5 billion years. After that, it will expand into a red giant and eventually shed its outer layers, leaving behind a white dwarf that will cool slowly over trillions of years. But the universe itself will last much longer. Current theories suggest the universe will continue expanding forever, eventually becoming so spread out and cold that no new stars can form. Existing stars will die, one by one, until the universe goes dark. This future, sometimes called the heat death of the universe, might occur in 10 to the power of 100 years. That's a 1 followed by 100 zeros, an unimaginably long time. Compared to this future, not only is Earth small in space, but our existence is brief in time. We exist for a cosmic instant on a cosmic speck. Earth's habitability isn't just about being in the right place. It's also about a series of cosmic accidents and near misses that shaped our planet into a world where life could not only begin, but thrive for billions of years. About 4.5 billion years ago, shortly after Earth formed, a Mars-sized object called Theia crashed into the early Earth. This collision was catastrophic. It vaporized huge portions of both worlds, sending debris into orbit around Earth. This debris eventually coalesced to form the Moon. This collision had several crucial effects. First, it tilted Earth's axis to about 23.5 degrees, giving us seasons. Without this tilt, Earth's climate would be much more extreme, with permanent ice caps reaching much farther toward the equator and making large portions of the planet uninhabitable. Second, the collision melted Earth completely, allowing heavy elements like iron to sink to the core, while lighter elements rose to form the crust. This differentiation was crucial for developing Earth's magnetic field. Third, it gave us the Moon, which stabilizes Earth's axial tilt and creates tides. If Theia had missed Earth, or if the collision had been too violent and destroyed Earth completely, we wouldn't be here. The impact needed to be just right. Too weak, and Earth wouldn't have a large moon. Too strong, and Earth would have been shattered. It was a cosmic lottery, and we won. Earth has also been lucky, with nearby supernovae. When massive stars explode, they release enormous amounts of radiation that can strip away a planet's ozone layer and sterilize any life on the surface. Astronomers estimate that a supernova within about 30 light-years of Earth could cause a mass extinction. The last nearby supernova was probably several million years ago, far enough away and long enough ago that it didn't significantly affect life on Earth. We've been in a quiet cosmic neighborhood, at least for the past few 100 million years. Even our star's stability matters. Some stars are variable, changing brightness dramatically over short periods. Others emit frequent superflares, massive bursts of energy that would fry any nearby planets. Our central star is remarkably stable, varying in brightness by less than 0.1% over its 11-year solar cycle. This stability has allowed Earth's climate to remain relatively stable over billions of years, giving lifetime to evolve. All these factors working together make Earth not just habitable, but stably habitable for billions of years. We're not just in the right place, we're also lucky, and that luck makes our planet rare, even if Earth-sized planets in habitable zones turn out to be common. Throughout this journey, we've focused on facts and figures, numbers and distances. But let's not forget the human element of exploration. Every spacecraft that's traveled to another planet was designed and built by teams of engineers and scientists. Every image from Mars or Saturn or Neptune was processed and analyzed by people who dedicated their careers to understanding these distant worlds. The astronauts who traveled to the Moon risked their lives to expand human knowledge. The engineers who guided Voyager past Jupiter and Saturn, keeping the spacecraft functioning despite being decades old and billions of kilometers away, showed remarkable skill and dedication. The scientists who spend years or decades working on a single mission, often waiting years between major mission milestones, demonstrate incredible patience and commitment. And the public, the ordinary people who fund these missions through their taxes and who follow the results with interest, they're part of this story too. Because space exploration is ultimately a human endeavor. We explore not because we have to, but because we want to, because we're curious, because we want to know what's out there. Despite all we've learned, there's still much we don't know about the solar system. Let's talk about some of the biggest mysteries. One mystery is the nature of Planet 9. Some astronomers think there might be a large planet, perhaps 10 times the mass of Earth, traveling in the outer solar system far beyond Neptune. They've noticed that several distant Kuiper belt objects have orbits that seem to be influenced by something heavy. The proposed Planet 9 could explain these orbits, but so far no one has found direct evidence of such a planet. Another mystery involves the formation of the solar system itself. We understand the broad outline. A cloud of gas and dust collapsed under gravity, forming our central star at the center and the planets in a disk around it. But many details are unclear. Why do the planets have the specific sizes and compositions they do? Why is there a gap between Mars and Jupiter, where the asteroid belt is instead of a planet? How did the giant planets migrate to their current positions? We also don't fully understand Jupiter's interior. Is there a solid core deep inside, or is it all gas and liquid all the way down? The Juno mission is helping answer this question, but we still don't have a complete picture. Saturn's rings are another puzzle. We're not sure how old they are or exactly how they formed. Are they ancient, left over from the formation of the solar system? Or are they relatively young? Perhaps the remains of a moon that was torn apart by Saturn's gravity within the last few 100 million years. We don't know for certain whether life exists anywhere else in the solar system. Europa, Enceladus, and Titan are all candidates with subsurface oceans or lakes that could potentially harbor life. But we haven't found definitive evidence yet. Future missions might drill through the ice on Europa or Enceladus to sample the water beneath, which could finally answer this question. We also don't fully understand our star's activity cycle. It goes through an 11-year cycle of increasing and decreasing activity, marked by changes in the number of sunspots and the frequency of solar flares. But we don't completely understand what drives this cycle, or why it's 11 years rather than some other period. These mysteries keep scientists busy. Each one represents an opportunity to learn something new about our cosmic neighborhood. We've spent this entire journey exploring our solar system, but let's take a moment to understand where our solar system fits in the larger universe. Our entire solar system, from our central star to the edge of the Oort Cloud, is just one tiny part of a galaxy called the Milky Way. The Milky Way is a spiral galaxy containing between 100 billion and 400 billion stars. Our central star is just one of these hundreds of billions. The Milky Way is about 100,000 light-years across. If you traveled at the speed of light, it would take you 100,000 years to cross from one side to the other. Our central star is located about 26,000 light-years from the center of the galaxy, roughly halfway out in one of the spiral arms. The Milky Way is part of a collection of about 50 galaxies called the Local Group. This includes Andromeda, the nearest large galaxy to us, which is about 2.5 million light-years away. The Local Group spans about 10 million light-years across. But the Local Group is just one small cluster in a much larger structure called the Virgo supercluster. The Virgo supercluster contains at least 100 galaxy clusters and spans about 110 million light-years. The Milky Way, along with the entire Local Group, is just a tiny part of this structure, and the Virgo supercluster itself is part of an even larger structure called Laniakea, which spans about 520 million light-years and contains about 100,000 galaxies. The observable universe, the part we can actually see, is about 93 billion light-years across. It contains an estimated 2 trillion galaxies. Each galaxy contains billions or trillions of stars, and around many of those stars circle planets. The total number of planets in the observable universe is almost impossible to comprehend. Estimates suggest there are at least 100 billion trillion planets. That's a 1 followed by 23 zeros. And our solar system? It's one system among billions of trillions, traveling through one galaxy among 2 trillion galaxies, spread across 93 billion light-years. When you think about it that way, our solar system is not just small, it's almost nothing. It's so tiny, so insignificant in the grand scheme of the universe that it barely registers. While we're discussing our place in the cosmos, it's worth examining the cosmic dangers that could affect our solar system. Understanding these threats gives perspective on how vulnerable our small corner of space really is. Asteroid impacts within our solar system are the most familiar threat. We've already mentioned the asteroid that killed the dinosaurs 66 million years ago. But that wasn't even the largest impact Earth has experienced. About 2 billion years ago, an asteroid estimated at 10 to 15 kilometers across struck what is now South Africa, creating the Vredefort crater, which is about 300 kilometers in diameter. Smaller impacts happen more frequently. The Tunguska event in 1908 flattened about 2,000 square kilometers of Siberian forest when a meteor, about 50 to 60 meters across, exploded in the atmosphere. If that same object had hit a major city, millions could have died. Gamma-ray bursts represent an even more catastrophic threat. When certain massive stars explode as supernovae, they can produce focused beams of intense gamma radiation. If a gamma-ray burst occurred in our galaxy and one of these beams pointed at Earth, it could strip away Earth's ozone layer within seconds. Without the ozone layer to protect us from ultraviolet radiation, the biological effects would be devastating. The terrifying thing about gamma-ray bursts is that they travel at the speed of light. There would be no warning. One moment, everything would be normal. The next moment, the sky would light up as bright as our star for a few seconds, and Earth's ozone layer would be gone. Fortunately, gamma-ray bursts are rare and require very specific circumstances. Astronomers estimate this might happen once every few 100 million years. It's possible that some past mass extinctions were caused by gamma-ray bursts, though we have no direct evidence. While we're discussing our place in the cosmos, it's worth examining the cosmic dangers that could affect our solar system. Understanding these threats gives perspective on how vulnerable our small corner of space really is. Asteroid impacts within our solar system are the most familiar threat. We've already mentioned the asteroid that killed the dinosaurs 66 million years ago, but that wasn't even the largest impact Earth has experienced. About 2 billion years ago, an asteroid estimated at 10 to 15 kilometers across struck what is now South Africa, creating the Vredefort crater, which is about 300 kilometers in diameter. Smaller impacts happen more frequently. The Tunguska event in 1908 flattened about 2,000 square kilometers of Siberian forest when a meteor about 50 to 60 meters across exploded in the atmosphere. If that same object had hit a major city, millions could have died. Gamma-ray bursts represent an even more catastrophic threat. When certain massive stars explode as supernovae, they can produce focused beams of intense gamma radiation. If a gamma-ray burst occurred in our galaxy and one of these beams pointed at Earth, it could strip away Earth's ozone layer within seconds. Without the ozone layer to protect us from ultraviolet radiation, the biological effects would be devastating. The terrifying thing about gamma-ray bursts is that they travel at the speed of light. There would be no warning. One moment, everything would be normal. The next moment, the sky would light up as bright as our star for a few seconds, and Earth's ozone layer would be gone. Fortunately, gamma-ray bursts are rare and require very specific circumstances. Astronomers estimate this might happen once every few 100 million years. It's possible that some past mass extinctions were caused by gamma-ray bursts, though we have no direct evidence. Rogue black holes present another exotic threat. Most black holes travel in orbits around the center of the galaxy along with everything else. But occasionally, gravitational interactions can eject a black hole, sending it wandering through space. If a rogue black hole passed through our solar system, its gravity would disrupt the orbits of the planets. Even if the black hole didn't directly hit Earth, it could alter Earth's orbit enough to make our planet uninhabitable. Earth could be flung out of the habitable zone, either freezing or cooking. Or Earth could be ejected from the solar system entirely, doomed to drift through interstellar space as a frozen, dark world. The chances of this happening are extremely small. Space is so immense, and even rogue black holes are rare. But it's not impossible. Solar storms pose a more immediate, if less catastrophic, threat. Our central star regularly ejects clouds of plasma called coronal mass ejections. When these hit Earth, they interact with our magnetic field, creating beautiful auroras. But they can also damage satellites, disrupt communications, and overload power grids. In 1859, the largest recorded solar storm, called the Carrington event, hit Earth. Auroras were seen as far south as the Caribbean. Telegraph systems worldwide failed, and some caught fire. If a similar storm hit today, it could cause trillions of dollars in damage by destroying transformers and electronics. Our central star is capable of producing even larger storms than the Carrington event. In 2012, a massive coronal mass ejection comparable to or larger than the Carrington event erupted, but fortunately missed Earth. If it had hit, experts estimate it could have knocked out power to large portions of North America and Europe for months or years. Then there's the possibility of nearby supernovae. When a massive star explodes, it releases enormous amounts of radiation. A supernova within about 30 light-years of Earth could damage or destroy our ozone layer. The good news is that there aren't many stars close enough and massive enough to threaten us. Betelgeuse will eventually explode as a supernova, but it's about 650 light-years away, far enough that the explosion will be spectacular to watch, but not dangerous. Finally, there's the long-term threat of galactic collisions. In about 4 billion years, the Milky Way will begin merging with Andromeda. This process will take billions of years. And despite the violence implied by the word collision, actual collisions between stars will be rare because stars are so far apart. However, the gravitational chaos could disrupt the Oort Cloud, sending billions of comets plunging into the inner solar system. Earth would face a bombardment lasting millions of years. All these threats remind us how fragile our existence is. Our solar system is small, isolated, and vulnerable to cosmic forces beyond our control. We've been lucky so far, living in a relatively quiet period, in a relatively safe part of the galaxy. But that luck might not last forever, and that's remarkable. In a universe that's mostly nothing, mostly cold, mostly lifeless, Earth is a place where life exists, where consciousness exists, where beings have arisen who can think, feel, create, and wonder about their place in the cosmos. Let's take a moment to appreciate the journey life has taken on Earth, because it puts our existence in perspective. Earth formed about 4.6 billion years ago from the same cloud of gas and dust that formed our star and the rest of the solar system. For the first few 100 million years, Earth was a hellish place. It was bombarded by asteroids and comets. The surface was molten rock. There were no oceans, no atmosphere suitable for life, nothing but heat and violence. Around 4 billion years ago, Earth cooled enough for liquid water to condense on the surface, forming the first oceans. Somehow, in these early oceans, life began. We don't know exactly how. The origin of life is one of the greatest unsolved mysteries in science. But we know it happened relatively quickly in geological terms. By 3.8 billion years ago, there's evidence of life in the form of simple, single-celled organisms. These early life forms were bacteria and archaea, simple cells without a nucleus. They lived in the oceans, probably near hydrothermal vents where chemical energy was abundant. For about 2 billion years, life remained simple. Just bacteria and archaea living in the oceans. But they were transforming the planet. Some bacteria evolved the ability to perform photosynthesis, using sunlight to convert carbon dioxide and water into sugars, releasing oxygen as a waste product. Throughout this journey, we've focused on facts and figures, numbers and distances. But let's not forget the human element of exploration. Every spacecraft that's traveled to another planet was designed and built by teams of engineers and scientists. Every image from Mars or Saturn or Neptune was processed and analyzed by people who dedicated their careers to understanding these distant worlds. The astronauts who traveled to the Moon risked their lives to expand human knowledge. The engineers who guided Voyager past Jupiter and Saturn, keeping the spacecraft functioning despite being decades old and billions of kilometers away, showed remarkable skill and dedication. The scientists who spend years or decades working on a single mission, often waiting years between major mission milestones, demonstrate incredible patience and commitment. And the public? The ordinary people who fund these missions through their taxes and who follow the results with interest, they're part of this story too. Because space exploration is ultimately a human endeavor. We explore not because we have to, but because we want to, because we're curious, because we want to know what's out there. Despite all we've learned, there's still much we don't know about the solar system. Let's talk about some of the biggest mysteries. One mystery is the nature of Planet 9. Some astronomers think there might be a large planet, perhaps 10 times the mass of Earth, traveling in the outer solar system far beyond Neptune. They've noticed that several distant Kuiper belt objects have orbits that seem to be influenced by something heavy. The proposed Planet 9 could explain these orbits, but so far no one has found direct evidence of such a planet. Another mystery involves the formation of the solar system itself. We understand the broad outline. A cloud of gas and dust collapsed under gravity, forming our central star at the center and the planets in a disk around it. But many details are unclear. Why do the planets have the specific sizes and compositions they do? Why is there a gap between Mars and Jupiter, where the asteroid belt is instead of a planet? How did the giant planets migrate to their current positions? We also don't fully understand Jupiter's interior. Is there a solid core deep inside, or is it all gas and liquid all the way down? The Juno mission is helping answer this question, but we still don't have a complete picture. At first, this oxygen was absorbed by rocks and dissolved iron in the oceans. But eventually, around 2.4 billion years ago, oxygen began to accumulate in the atmosphere. This was the Great Oxidation Event. It was catastrophic for most life at the time because oxygen was toxic to them. But it created opportunities for new forms of life that could use oxygen for energy. About 2 billion years ago, something extraordinary happened. A larger cell engulfed a smaller cell, but instead of digesting it, they formed a partnership. The smaller cell became the mitochondria, the power plant of the cell, while the larger cell provided protection and resources. This was the birth of eukaryotic cells, complex cells with a nucleus and specialized structures. All complex life, all plants, animals and fungi are made of eukaryotic cells descended from this ancient partnership. But life remained single-celled for another billion years. It wasn't until about 600 million years ago that multicellular life really took off. This was the Ediacaran period, when the first complex multicellular organisms appeared. Then came the Cambrian explosion about 540 million years ago. In a relatively short period, maybe 20 million years or so, most of the major groups of animals we see today appeared in the fossil record. Fish appeared about 500 million years ago. Plants colonized the land about 470 million years ago, followed by insects and other arthropods. Amphibians crawled out of the water about 370 million years ago. Reptiles evolved about 320 million years ago. Dinosaurs dominated the land for about 165 million years, from about 230 million years ago until 66 million years ago. Mammals had existed alongside dinosaurs, but they were mostly small creatures living in the shadows. When an asteroid struck Earth 66 million years ago, it caused a mass extinction that killed the dinosaurs and many other species. But it also created opportunities for mammals. They diversified and grew larger, filling the ecological roles left empty by the dinosaurs. Primates, the group that includes monkeys, apes, and humans, evolved about 55 million years ago. The first apes appeared about 25 million years ago. The human lineage split from chimpanzees about 6 to 7 million years ago. Our genus, Homo, appeared about 2.8 million years ago. Anatomically modern humans, Homo sapiens, appeared in Africa about 300,000 years ago. For most of that time, we lived as hunter-gatherers in small groups. Agriculture was invented only about 10,000 years ago. Writing was invented about 5,000 years ago. The Industrial Revolution happened about 250 years ago. Computers were invented less than 100 years ago. The internet became widely available only about 30 years ago. In cosmic terms, humans have existed for the blink of an eye. All of recorded history is a fraction of a fraction of a percent of Earth's history. And Earth's history is only about 1/3 the age of the universe. Yet in this brief time, we've accomplished something remarkable. We've developed consciousness, language, culture, science, art, music, literature. We've figured out where we are in the universe. We've sent machines to other planets. We've looked deep into space and seen galaxies billions of light years away. We've uncovered the history of the universe, from the Big Bang to the present day. The fact that our solar system is small doesn't diminish this. If anything, it makes it more impressive. Against all odds, in this tiny corner of space, life arose. And it didn't just arise. It evolved, diversified, and eventually produced creatures capable of understanding the universe. Despite our solar system's tiny size, humans have tried to make our presence known to the universe. These efforts reveal something profound about human nature. Even knowing how small we are, we still want to reach out, to say, "We exist," to anyone who might be listening. In 1974, astronomers used the Arecibo radio telescope in Puerto Rico to send a message toward the globular star cluster M13, about 25,000 light-years away. The message, known as the Arecibo message, consisted of 1,679 binary digits encoding information about human DNA, our solar system, and the shape of a human. The message will take 25,000 years to reach M13, and if anyone there responds, we won't hear back for another 25,000 years. The Pioneer 10 and 11 spacecraft, launched in 1972 and 1973, each carry a gold anodized aluminum plaque. These plaques show images of a human man and woman, the position of our star relative to nearby pulsars, and a diagram of our solar system showing Pioneer's origin. Both spacecraft have now left the solar system and are heading into interstellar space, carrying these messages as ambassadors from Earth. The Voyager 1 and 2 spacecraft, launched in 1977, carry golden records. These 12-inch gold-plated copper discs contain sounds and images selected to portray the diversity of life and culture on Earth. There are greetings in 55 languages, music from different cultures and eras, including Bach, Chuck Berry, and traditional songs from around the world, and sounds of Earth, waves crashing, birds singing, a mother's first words to her newborn child. The golden records also contain 116 encoded images showing mathematical and physical quantities, Earth's continental geography, photos of people from various cultures, images of animals, plants, buildings, and even a photo of a woman in a supermarket. Carl Sagan led the team that assembled this collection. He wanted to show any alien intelligence not just what humans look like, but who we are, how we live, what we value. Both Voyager spacecraft have now entered interstellar space, more than 20 billion kilometers from Earth. They're moving at about 17 kilometers per second relative to our star. At this speed, they'll drift through the galaxy for billions of years. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445 in the constellation Camelopardalis. In about 300,000 years, Voyager 2 will pass within about 4 light-years of Sirius. The chances of either spacecraft being found by an alien intelligence are vanishingly small. Space is immense. The probes are tiny. They're not broadcasting their location. An alien civilization would have to stumble across them by pure chance. And even if they did, the spacecraft's plutonium power sources will have long since decayed. The probes will be dead, silent, drifting through space. But that's not really the point. The golden records weren't launched with a realistic expectation of being found. They were launched as a statement, a message in a bottle thrown into the cosmic ocean. They say, "This is who we are. We exist, we thought, we felt, we created, we loved. We reached out into the darkness hoping someone might find this and know that we were here." In a way, these messages are more for us than for aliens. They force us to think about what we want to say about ourselves. What's important? What defines humanity? What should we preserve? The process of creating these messages makes us reflect on our own nature. These spacecraft also represent humanity's first attempt at physical immortality. Long after Earth is gone, Engulfed by the red giant our star will become in 5 billion years, these spacecraft will still be drifting through space. They'll outlast our planet, our civilization, perhaps even our species. They're time capsules carrying evidence that we existed, that we thought and felt and reached for the stars. Even if no alien ever finds them, even if they drift through space until the heat death of the universe, they'll still be there. Silent testimonies to a species that looked up at the stars and wondered. In a way, these messages are more for us than for aliens. They force us to think about what we want to say about ourselves. What's important? What defines humanity? What should we preserve? The process of creating these messages makes us reflect on our own nature. These spacecraft also represent humanity's first attempt at physical immortality. Long after Earth is gone, engulfed by the red giant our star will become in 5 billion years, these spacecraft will still be drifting through space. They'll outlast our planet, our civilization, perhaps even our species. They're time capsules carrying evidence that we existed, that we thought and felt and reached for the stars. Even if no alien ever finds them, even if they drift through space until the heat death of the universe, they'll still be there. Silent testimonies to a species that looked up at the stars and wondered. Let's also appreciate how we came to understand our place in the universe, because this journey itself is remarkable. For most of human history, we thought Earth was the center of everything. Ancient civilizations believed the Earth was flat, with the sky as a dome overhead. This made sense based on what people could observe. The ground beneath their feet felt solid and stationary. The sky appeared to rotate around them. Greek philosophers like Aristotle argued that Earth must be at the center of the universe because it was the heaviest element, and heavy things naturally fall toward the center. This model, called the geocentric model, dominated thinking for nearly 2,000 years. In the 2nd century, the astronomer Ptolemy created a detailed mathematical model of the geocentric universe. His model could predict the positions of the planets with reasonable accuracy, which seemed to confirm that Earth was indeed at the center. But there were problems with the geocentric model. The planets didn't move in simple circles. They would speed up and slow down, and sometimes even appear to move backwards in the sky. To explain this, Ptolemy had to add epicycles, circles upon circles, making the model increasingly complicated. In the 1500s, a Polish astronomer named Nicolaus Copernicus proposed a radical idea. What if our star, not Earth, was at the center? What if Earth was just another planet traveling around it? This heliocentric model could explain the planet's motions more simply. But it was controversial because it contradicted both common sense and religious teachings that placed Earth and humanity at the center of God's creation. Copernicus published his ideas in 1543, shortly before his death. His model didn't immediately catch on, partly because it wasn't much more accurate than Ptolemy's model at predicting planetary positions. But it planted a seed. In the early 1600s, the German astronomer Johannes Kepler refined the heliocentric model by showing that planets travel in ellipses, not perfect circles. This made the model much more accurate. Around the same time, the Italian astronomer Galileo Galilei used one of the first telescopes to observe the night sky. He discovered moons circling Jupiter, which showed that not everything went around Earth. He saw that Venus went through phases like the moon, which only made sense if Venus circled our star, not Earth. The geocentric model was crumbling, but the final blow came from Isaac Newton, who in 1687 published his laws of motion and universal gravitation. Newton showed that the same force that makes an apple fall from a tree also keeps the planets in orbit. The heliocentric model wasn't just observationally correct, it was physically correct, based on fundamental laws of nature. But this was just the beginning of knocking humanity off its pedestal. In the 1700s and 1800s, astronomers realized that the solar system was just one part of a much larger structure. The Milky Way wasn't a small band of clouds. It was a huge collection of stars, and our star was just one of them, located far from the center. In the early 1900s, there was a debate about what those fuzzy spiral nebulae were that astronomers could see through their telescopes. Some thought they were clouds of gas within the Milky Way. Others thought they were island universes, separate galaxies far beyond the Milky Way. In 1924, Edwin Hubble settled the debate by measuring the distance to the Andromeda Nebula. It was over 2 million light-years away, far beyond the Milky Way. Andromeda was indeed a separate galaxy. This meant the universe was much, much larger than anyone had imagined. The Milky Way was just one galaxy among many, but Hubble made an even more startling discovery. He found that most galaxies were moving away from us, and the farther away they were, the faster they were receding. The universe was expanding. This discovery led to the Big Bang theory, the idea that the universe began in an extremely hot, dense state about 14 billion years ago and has been expanding ever since. So, in just a few hundred years, we went from thinking Earth was the center of everything to understanding that we're on a planet traveling around an ordinary star, in an ordinary galaxy, in an expanding universe that began nearly 14 billion years ago. Each discovery made us smaller, less central, more ordinary, and yet each discovery was also a triumph. We figured this out ourselves through observation, reasoning, and mathematics. No one handed us the answers. We had to work for them, sometimes fighting against prevailing beliefs and our own intuitions. The fact that we could discover our own cosmic insignificance is itself significant. It shows that even though we're small, we're capable of understanding our place in the immensity. We're capable of looking up at the stars and figuring out what they are, how far away they are, how they work. That's extraordinary.